So, ooh, so these are just some funsies, pictures. These cups are acting like converging lenses, so they're doing an inverted. The right and left are inverted. Okay, cool. Okay, so raindrops, water drops act like converging lenses. So like there's a rose in every raindrop there. Try it. Just pull up to an American flag on a rainy day and look at the raindrop. Real close. That's cool. See if you can figure out how they did that one. Okay. So they turned the map upside down, dripped the water, and then turned the picture upside down. So it looks right side up. Okay. All right. So my assumption is the most applicable part of lenses is corrective vision stuff for your lives. So let's talk about how the eyeball works. Okay. So you have a lens in your eye. It's a converging lens, and what it does is it makes a real image on the back of your retina, just like we did with the magnifying glass and the piece of paper. And you're trying to like find that place where it created an image on the piece of paper. Okay. The catch though is your eyeball can't do this. Can't adjust the distance because otherwise your eyeball will be like, be like crazy. Okay. I don't think so, but good question. Is that what snails do? Um, so what that does to be able to focus on different objects is different distance away. It actually your lenses and your eyes actually constrict and relax, and it changes the focal length. It changes the radius of curvature of the lens itself. Okay, so when you see something far away, your lenses are relaxed and it forms an image. Okay, if the object is close, you have to contract the lens, flex the muscles, and that causes the refraction to bend more severely, refract more, like a bigger change in direction. Okay, so it decreases the focal length. That's pretty cool. We're going for an image in the back there. Okay, Maddox. Does that mean we see things upside down? In a way, yes. It forms a real image on the back of our retina. Our cones and rods send signals to our brain. Our brain flips it right side up. That makes sense. Some people. No. No. It makes it so. No, doesn't change reality. It just your brain interprets it. You're not hanging off the ceiling. I've 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 heard, and I don't know if this is right or not, but I've heard that babies, their brain hasn't done that yet, and so they see everything upside down. I don't know if that's totally valid. Because we're not. We're on the floor. Like everything goes down. Everything doesn't go up. All right. Sorry I brought that up. All right. It's just the image, not the actual physical thing. Just how we perceive it. Our brains compensate for the fact that our retinas register it upside down. Good with that? Okay. All right. So I am not talking about dilation of the pupils. I am talking about lenses. Okay, so your pupil dilation, that is the black thing in your eyeball that is getting bigger or smaller depending upon how much light there is. Okay, so the best way, or the most apparent memory in my brain was like going in and out of recess. Like when you go out on a sunny day, it's like, oh, so bright, and your eyes are adjusting or contracting, like the pupils are constricting to let in less light. But then when you go back inside, it's like, everything's all fuzzy, gray, bluish, and you're like trying to see, and your pupils are going to dilate to let in more light. If you ever get people think you might have got a concussion, they'll shine a light in your eye to see if your pupils are dilated. What should happen is your pupils should constrict, making it smaller. But if they stay big and dilated, you're like, you need to go check out a doctor. You probably have a concussion. Okay, so that's what people are doing when they shine a flashlight in your eye. Okay, this is not the lens. This is just in a camera vernacular, the aperture. Okay, it's how much light is being let in. So nearsighted and farsighted. This terminology focuses on what you can do. It does not highlight what you can't do. Okay. So when someone says, "Oh, you're nearsighted," that means you can see things close. You are nearsighted. Yes, you are. Attaboy. Like, woo, yes. Let's not talk about things far away. Let's just focus on what you can do positive. You can see things near. You're nearsighted. Okay. So what that means is your lens is not relaxing enough. And so the image is, the rays are converging too soon. Does that make sense? You need to spread those rays apart just a tad bit so they actually converge to the right spot. Now, to spread those out, we're going to use a diverging lens to spread it out a little bit. Now, but if we did one of those lenses, that would not help at all. So, a divergent lens for glasses looks something like this, where it's a little bit thicker on the outside than it is in the middle. Does that make sense? Okay. This is the yep, middle one. Okay. So we're going to spread this ray out just a tad bit so that it converges at the retina. Does that make sense? Okay. Versus farsighted, you are eagle eye. But let's not talk about reading a book. Okay. Anything up close. You can't see up close. You can see far away. Your lens is not constricting enough. These muscles are not contracting enough to bring the rays to converge at the retina. So you need help. Now, one of those is going to be a little too aggressive, but what you're going to have, the glasses are going to be a little thicker in the middle than they are on the outside. And that's going to bring the rays together sooner. Okay, good with that? Contact lenses, the same thought is applied. You just bring, they just have the material of the contact lenses a little thicker in the middle than it is on the outside. And then they got extra stuff to like suck to your eyeball, like a suction cup. Does that make sense? And then for a divergent lens, it's just a little thinner here and a little thicker there. JP. The optical nerve. Yeah, the optical nerve. So, yeah. Good question. So bifocals have, I'm not sure how to draw this, but bifocals, the glasses, it's a diverging here. This is for nearsighted, so to help you see far away. The part down here is for farsighted to help you see close. So back in the day, like my grandparents, they would have a little window here that you could see. Okay. Now they've blended it, so it's not as an apparent thing. Okay. So, astigmatism. What this is your eyeball looks more like an egg than a ball. So there's some oblongness. So is that like when lights like stretch? Could be, yeah. It's like, because like anytime I'm driving an accident like that, all the lights like. Yep. That's what it is. Yep. So you can get glasses, contacts to get that fixed. Okay. I can still drive. Even if someone has perfect vision, are they still okay, say it again. So even if someone has like perfect vision, yeah. Are they still dominant in their farsighted? I don't know. Good question. I don't know. So, if this is intriguing to you, optometry, physics. Okay. What? It's like only at night, and it's more apparent whenever it's like raining. Yeah. All right. Okay, last thing, and then we'll do the lab quiz. Why is the sky blue? It is not because the ocean reflects light. Okay. Here we go. Ready? I've got lots of little conversations that need to like. Here we go. So, our atmosphere is made up of mostly nitrogen. Nitrogen is a fairly small molecule. It's like 78% nitrogen. Okay. Nitrogen happens to resonate with the higher frequencies of light. It has a natural frequency that's really close to blue. And that is why our sky is blue. So what happens is this. Light, white light from the sun goes through our atmosphere. Now, I drew the atmosphere crazy exaggerated thickness wise. Okay. Now, blue light and purple are scattered. Okay. So nitrogen scatters, that's the word or the verb we use, scatters higher frequencies of light into blue and purple. Okay. What it doesn't scatter is green. We're going to call this yellow, orange, and red. What color do we see the sun as we look at it? Yellow. What does red and green make? Yellow. Good at that? JP. Great question. Because it has whatever is the substance, H2O, we'll say, reflects blue light and absorbs red and green. But it has to be like a lot of it, otherwise it's just transparent. Like it has to be a certain depth or thickness. And like other things like green are gonna have like algae in them. The Wabash has a lot of mud in it and other stuff that I don't want to drink.
Why is the sky like sometimes not very blue at all, and then other days it's like
really good question. I'll get to that in 5 minutes.
Why are like sunrises and sunsets?
Beautiful question. I'm going to get to that in 30 seconds. Okay. All right. So these slides tell you just what I just told you. So here, this is a graph of different frequencies and how intense they are. So this is sunlight from the light from the sun. Our sun is a yellow star. We have the most intense light is like in the greenish, yellow, blue. Okay, and so this is combination of that is chartreuse. This is where you get the day glow. Okay, it's capitalizing on the fact that you have the highest, most intensity at that wavelength. Okay. All right, so what would happen if our atmosphere was made up of something bigger than nitrogen? Okay, so the larger the molecule, the lower the frequency of light is scattered. The bigger the molecule, the lower the frequency of light is scattered. Correct answer is B. So green's going to get scattered, and what's left over would be yellow, orange, and red. So it's going to look more orangish. Okay. So, yep. Mm-hmm. No, you need like the order, like Roy G. Biv. Yeah.
Like the red, the blue,
No, I'll give it to you. I'll give that to you.
It's so cool for a sky.
Yeah.
I feel like if the grass in the sky matched, it wouldn't be very
Purple.
Okay, that's low.
because then when you draw pictures, the grass and the sky would be together.
Okay, so what about sunsets? So here's how that works. So in order to see the sunset, you're kind of like on the edge there, and light from the sun has to go through a whole bunch more atmosphere than it did here. Does that make sense? And the likelihood of hitting some other molecule that's bigger than nitrogen is way higher. Okay? Like the size of the molecule determines which frequency gets scattered. The chance of you hitting something other than nitrogen as you go through here is much higher, and so that's what happens. And so you get your purples and your blues scattering, but you also get your greens and your yellows and some of your oranges. And what gets through is orange and red, the lowest frequencies, longest wavelengths. And so the color of the sky is this, and the color of the sun is that. And that's why as the sun gets lower in the horizon, it becomes deeper and deeper red. Okay, or orange. Okay. And so you get cool sunsets. You actually get more impressive sunsets as there's more junk in the atmosphere, upper atmosphere. Okay. So if a volcano goes off in the Pacific, or there's a forest fire in California and put a whole bunch of junk up in the atmosphere, we see some really cool sunsets. Okay. Refraction, I don't worry about that. All right, so the harvest moon. Don't stress, you're fine. The harvest moon happens when the moon is near the horizon. As this rises up in the sky, it becomes more white. And this does the same thing as the sunset is doing. It's going through more atmosphere. And the last thing.
So does the moon shine reflecting the light off the sun?
Yep. So the last thing, clouds have a bunch of different molecules, sizes, so they scatter a whole bunch of different frequencies of light, so they look white. Our summer days in the Midwest look whitewashed, versus out west when it's more arid, less humid, skies look like this. This is because the water molecules in our atmosphere, due to humidity, scatter different frequencies, and it makes it look more white than the crisp blue. This happens, we see this after the rain, where it gets the humidity out of the sky, and so we'll see a brighter blue after rainstorms. Good with that? Okay. Remember, you got a reading quiz, not reading quiz, a review worksheet due tomorrow. Lab quiz, move, stay, move, stay, move, stay.